Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Introduction General Characteristics of Shape Memory Alloys from the paper Functional Materials. So students, let us see what we are going to study in this module. First, the concept of shape memory effect. Second, we will discuss the general characteristics of shape memory alloys. Next, we will discuss the one-way and two-way shape memory effect. Finally, we will also discuss the phase transformations exhibiting the shape memory alloys. So, let us start with a basic introduction about this module. Functional materials are a very large class of material, and it is not at all possible to cover all the different classes of materials here. However, there are certain broad classes of material that exhibit special characteristics and their fundamentals are similar. In this module, we will cover one such class of material which are called as shape memory alloys. Although we use the word alloy, shape memory effect has also been observed in polymers and ceramics. The properties exhibited by them may seem similar at the application level. However, the mechanism at the atomistic level is very different. For example, metals are crystalline materials, and shape memory effect in metals is governed by a special kind of interface between these crystallites called as twin boundaries. On the other hand, shape memory effect observed in polymers is very different in nature, as it does not have long range crystallinity. In this module, we will focus only on the metals and the alloys. Shape memory alloy. An alloy that remembers its shape between two states. Let us take an example. You give the material a shape at state 1 and then take the material to state 2. Now you change the shape or deform it in state 2. If this deformation or this deformed material is taken to state 1, then it regains its shape. This is called as shape memory effect SME, and the material is called as shape memory alloy. This figure shows the example of one-way shape memory effect. So students, as noted from the figure, that if you give any change of state of the material, for example austenitite to martensite, the material dimension changes nominally. That is, it changes to the shape, to the state 1. Now if we changes the state 1 to state 2 and then it gets deformed to any shape, then finally the change state of the material, that is from martensite to austenite, the material regains its original shape. So this whole figure depicts the one-way shape memory effect. A real application of this effect is shown in this figure. Here, a space antenna, which is nothing but made up of titanium nickel wires, is shown in the deformed state. As shown in the figure A, when this material is heated above a critical temperature, it starts to transform into another state where it remembers its shape, and so it's start to expand, which is clearly depicted in figure B and figure C. Then finally it takes the full shape as shown in the figure D. It must be ample clear from the schematic and the real life example that the two states are nothing but the crystalline or the phase state at two different temperatures. So this figure shows another example of shape memory effect. However, this is made out of a polymer. Now, as it can be seen in this figure, the effect exhibited is similar to that alloy, but as mentioned earlier, the underlying mechanism is very different. So this figure shows a polymeric material showing the shape memory effect. The figure A shows a permanent shape at room temperature. The figure B shows a temporary shape again at RT, and then the next figure C shows the shape recovery at 40 degrees Celsius. Now finally, when the temperature reaches to 50 degrees Celsius, the shape recovers fully itself. Shape memory alloys. Let us see some of the examples of these type of alloys. Commercial alloys like nickel titanium, copper zinc aluminium, copper aluminium nickel. Other alloys are iron manganese silicon, silver cadmium, gold, cadmium, copper, tin, copper, zinc, indium, titanium, nickel, aluminium, iron, platinum. So, the basic applications of these alloys are: first, force actuators, that is, they exert force over a considerable range of motion. In the joining, that is, in cylindrical sleeves joining tubes. Third one, they are used in proportional control, that is, the valve controls the rate of fluid flow by careful heating. Lastly, the most important application is in super elastic. The SMAs, they display super elastic behavior. This will be explained later on. General characteristics. As mentioned earlier, shape memory alloys exist in two different states, that is, crystalline state or phases. Usually, it is in austenite phase at higher temperature and martensite phase at lower temperature. For example, in nickel titanium alloy, the shape which is given to austenite phase is the one that alloy remembers, even if it is deformed in low temperature martensitic phase. This transformation of state can be understood in the terms of the plot shown in the figure. So this figure shows the phase transformation with temperature, that is, the variation of the length with temperature and its relation with the physical characteristics. Now, as clear from the figure, the y-axis on the right side shows the percentage of martensite for a given temperature, and as we can see that there is a hysteresis on moving from the parent phase, that is high temperature phase, to the product phase, which is nothing but the low temperature phase or martensite. So now if we start from a temperature much above AF as shown in the figure and start to cool down, then the first martensite would appear near the MS temperature and transformation would be complete when the temperature is lowered to MF. Similarly, when we take a material which is at temperature below MF and start to heat it, then during heating, parent phase will start to appear at As, and the transformation would be complete when temperature reaches the AF. So, there are two important things to notice here, which is one, that when heating and when cooling, the fraction of martensite and austenite are not the same, meaning there is a hysteresis. Secondly, that the fraction of martensite is dependent only on the temperature but not on the time. This is because these transformations are diffusionless, or they are also called as military transformations. The temperature difference between the transformations T1 or hysteresis is usually small, which allows it to be reversible. If this temperature difference is very large, then the driving force required for the transformation is very large and the transformation is not reversible. So, students, as noted from the previous figure, there are four important temperatures from the point of view of shape memory effect, which is MS, MF, AS and AF. MS and MF are nothing but the start and the finish temperatures respectively when cooling from austenite phase to transform to martensite phase. Hence, MS is always greater than MF. Here, AS and AF are start and finish temperatures when heating from martensite phase to transform to austenite phase. Hence, AS is always less than AF. So the maximum temperature at which SMAs can no longer be stress induced, that is, shape memory alloys can no longer be stress affected, is denoted by MD. Steel also forms martensite and austenite. So, the question arises, is it the SMA? The answer is no. If the temperature difference between the two phases is too large, then the driving force is also very large and the process does not remain reversible anymore. So, the phase transformation with temperature is no longer a hysteresis curve. The temperature difference between austenite and martensite phase of carbon steel alloy is approximately 700 degrees Celsius. Hence, carbon steel does not exhibit the shape memory effect. One-way memory effect versus the two-way memory effect. Now students, previous examples shows one-way memory effect. Here the alloy can be deformed in its low temperature state and it will regains the original shape upon heating to high temperature state. However, when the alloy is cooled again, it will retain this original shape until it is deformed again. So deformation is necessary to create low temperature shape. On heating, transformation starts at AS and is completed by AF. So the cooling does not lead to any major shape change. So one-way memory effect versus two-way memory effect tells us that two-way memory effect, as the name suggests, shows shape change while heating and cooling. The material remembers two different shapes. One is at the lower temperature and the other at higher temperature. However, a component showing two-way memory will lose this effect when heated beyond a certain point to the austenitic state, that is, it regains its original shape or at least close to it. The D figure shows that on cooling again to martensitic state, no change takes place for one-way shape memory effect, but on the figure on the right hand side, which exhibits a two-way shape memory effect, the material changes or regains the shape obtained in the martensitic state or at least close to it. So the figures on the left hand side, they shows the one-way shape memory effect, and the figures on the right hand side shows the two-way shape memory effect. Transformations. Solid state phase changes are usually thermally activated. Phase transformations can be classified into the following main classes. First, precipitation reactions, where alpha prime changes to alpha plus beta. This happens when a supersaturated phase or alpha prime transforms to the stable phase, that is alpha, along with another phase, that is beta, which is called as the precipitate phase. Second type of transformation is eutectoid transformation, where gamma changes to alpha plus beta. This occurs when one solid phase, that is gamma, which is metastable, transforms to the two stable solid phases, that is alpha plus beta. Third one is ordering reactions, where alpha disordered changes into alpha ordered. In this kind of reaction, there is only change in the relative positioning of the atoms. In the disordered state, there is usually mixing of position between two or more different types of atoms. In the ordered state, a particular element takes a particular position within the lattice. Next type of transformation is beta to alpha. In this kind of transformation, the parent phase transforms to the product phase without any change in the composition, but with different crystal structure. Finally, the polymorphic changes. Transformations in single component system, when different crystal structures are stable over different temperature ranges. So now phase transformations can be broken into two major steps, which are nucleation and growth. Now, nucleation can again be classified as homogeneous and heterogeneous nucleation. Like solidification reactions, the phase transformations also occur preferably by heterogeneous nucleation. This can be understood in terms of the energy between the two processes. Homogeneous nucleation. When the product phase forms within the matrix of the parent phase, then we can say that this is homogeneous nucleation. Formation of interface leads to an activation energy barrier. So here the energy changes are associated with first the volume free energy, second the surface energy, and third is misfit strain energy. So we can say that delta G is equal to minus V delta GV plus delta gamma plus V delta GS. Like solidification transformation, there is a critical radius and critical energy barrier. It can be shown that a critical undercooling is required before the nucleation can take place. Homogeneous nucleation. So students, this graph shows the change in surface energy, volume free energy, and total free energy with the change in the size of homogeneous nuclei. In the materials, whenever there are suitable nucleation sites present, like excess vacancies, dislocations, grain boundaries, stacking faults, inclusions, nucleation preferably occurs over there. Creation of nucleus actually results in annihilation of defects and hence lowering of energy. Thus, heterogeneous nucleation is vastly favored over homogeneous nucleation. Energy change associated with heterogeneous nucleation is given by delta G heterogeneous equal to minus V multiplied by delta GV minus delta GS bracket close plus A gamma minus delta GD. The phase transformations that we have discussed mostly involve the movement of atoms or some kind of diffusion. However, there is a completely different kind of transformation and it is called as diffusionless transformation, and martensitic transformation is one example of this kind. So students, let us summarize what we have learned in this module. The materials exhibiting the shape memory effect are shape memory alloys which regain their shape when they are deformed. Secondly, nickel titanium alloys, copper zinc aluminium, and copper aluminium nickel alloys are the commercially available shape memory alloys. Thirdly, the shape memory alloys exist in two different states, that is, austenite phase at higher temperature and martensite phase at lower temperature. Fourth, there are two types of shape memory effect, that is one-way and two-way shape memory effect have been discussed. Fifth, various phase transformations have been discussed and they can be broken into two major steps, which are nucleation and growth. Lastly, we also discussed about the homogeneous and heterogeneous nucleation. Thank you.